is with minimal wave evaluating G prime domain.
Okay, so I'd like to thank the organizers for giving me the opportunity to give this talk. So this based on this recent paper done in collaboration with the other members of NCTS. Okay. So this is the outline of my talk. So I'll give a brief introduction about the situation of these B to SLL anomalies. Then I'll discuss how these anomalies can be addressed in a Z prime model. In this case, the Z prime model has MFV, minimal wave violating interactions. And then I'll discuss constraints on these on the couplings of this Z prime, and discuss the allowed parameter space and make some prediction. And then I'll finish with conclusions. Okay, as many in the audience know, the current B to SLL data have intriguing tensions with the standard model. And these tensions are mostly coming from LHCb recent measurements of these exclusive B to SLL, B to S mu mu especially decays. For instance, the branching ratio measurements of these decays mostly favor values below the standard model predictions. And then there's also some tension in one of the observable, angular observables in B2K star mu plus mu minus decay. But it's mostly, this tension is also observed by the Bell experiment, although the statistical confidence is low. Now, most interestingly, we have these ratios of branching fractions of these decays and also of these decays, which are actually in the standard model is almost 1. And so these ratios are quite clean observables, quantities, and so they are sensitive to new physics effects. And the LHCb also noticed, measured some discrepancies between the data and the standard model prediction. And so these are intriguing tensions with the standard model in the LHCb measurement mostly, and also in the Bell measurements. Now, these are not yet conclusive of new physics, these anomalies, because of their still low statistical significance. But interestingly, after these measurements, a number of people did global analysis of the B2SL data, and they showed that new physics can account for these anomalies probably at the 4 sigma level. But so we have to wait until we have more data to make some more conclusive statements about these anomalies. But it's interesting that new physics can account for these anomalies. And so after this measurement and this analysis, many theory papers have been written to discuss some possibilities. And so in this case also, we assume that these anomalies come from new physics. Now, from this global analysis, one of these, the best fits to the data results from new physics contributing via this quark-lepton interactions. And the CI here, C9 and C10 are the Wilson coefficients. And this analysis suggests that the new physics enter mostly in the muon channel, so L equal to mu channel, with these the sizes of the Wilson coefficients. And the electron channel, the preference is that the new physics is vanishing for 0. Okay? And the standard model contributes universally to these different channels. But new physics is suggested to be in the muon channel. Okay, so if that's the case, then there are in general 2 different operators that can contribute to those interactions, that can generate those interactions. So we can write down these two operators, and so they have leptons and quark operators. So in this case, L and Q are the lepton, contain the lepton doublets from the three families, and the deltas here are generally complex 3x3 matrices in flavor space. Now, people also consider some other possibilities for these operators, for example, pseudoscalar or scalar operators or tensor operators, but it turns out that those are not favored by the data as these other people analyzed or suggested. Now, in general, you can have a little more specific scenario where you consider these operators in the framework of what people call minimal flavor violation. And so you can do that, and you can account for the anomalies quite reasonably. So in this case, you can, for example, implement this idea of minimal flavor violation, which I will explain more shortly, in both the quark and lepton parts. But in this case, you can do that without considering the underlying new physics. So in this work, we want to consider a little bit more specific situation where we will consider some scenario of new physics. In this case, is the Z prime. So I will discuss also shortly. Okay, so let me first discuss briefly what minimal flavor violation, the idea of minimal flavor violation is. So as many know, also as we all know, the standard model has been very successful in describing the current data on flavor changing neutral currents and CP values in the quark sector. Okay, and so this motivates people to propose this hypothesis of minimal flavor violation, or MFV, for quarks. So this hypothesis states that Yukawa couplings are the only sources for the breaking of flavor and CP symmetries. Okay? And so you can implement this in a very specific model, as some of these people did also a long time ago. But you can also do it model independently by considering effective field theory with minimal flavor violation imposed. And so some years ago, these people also suggested that. And so if you do that, then in general, the new physics scale can be not too high. Because if you consider a generic flavor violating possibility, the data implies that the new physics scale would be very high. So it will be unreachable by current or near future detectors. But if you impose this minimal flavor violation, then it's possible that the new physics level or scale is reachable by our detectors, current detectors. Now you can, this was proposed in the quark sector, but you can extend this idea of MFV to the lepton sector. Okay. Now, in the lepton sector, we do not know much about the origin of the neutrino mass, and also we do not know the nature of neutrino mass, whether it's direct or Majorana mass. And so there are some ambiguities in the lepton sector if you want to implement MFV. And so that means if you want to extend the MFV idea to the lepton sector, you need to make some specific assumption about how you generate neutrino mass. Okay, so in this work we consider, as I said, a Z prime boson scenario with MFV in the Z prime fermionic couplings. Okay? So we impose MFV on both the quark and lepton sectors. And as I mentioned, because of the ambiguities, you need to make some assumption about how you want to generate the neutrino mass. So in this case, we consider the canonical type 1 seesaw mechanism, which has three generate heavy radioactive neutrinos. So this is a specific scenario that we will consider. Yes?
Did you specify the similarity content of the Z prime, or you deal with it as a more generally?
Oh, we have some specific assumptions of the Z prime coupling. Yes. This MFV idea, I will explain shortly. Okay, so let me consider how you implement this MFV a little bit more. So suppose in this case we assume the standard model plus 3 heavy right-handed neutrinos. So if you turn off all the mass terms in the Lagrangian, then the Lagrangian, or in this case the kinetic terms, the Lagrangian has this form, and this has actually a big flavor symmetry, because then you can make this rotation, global flavor rotations, and this Lagrangian is invariant under these flavor rotations. Okay. But now of course, the Lagrangian should have mass terms, and so in this case, if you turn on the mass terms, you have these Yukawa terms. In this case, the right-handed neutrinos has also this Majorana mass term. So if you turn on all these masses, these flavors, this big flavor symmetry is broken. But if you assume that the Yukawa couplings are actually spurions, which transform in this form, then you can restore at least most of these flavor symmetries. Okay. And so this gives us some idea about how you want to implement this idea of MFV. Yeah, because in this case, we want to rely on the Yukawas as the sources of flavor violation. Okay, so it's convenient to work in the basis where the Yukawas of the down-type fermions are diagonal. So that's what we have here. So in this case, the quark doublet will have this form, and the lepton doublet will have this form. And so this is the CKM matrix, this is the PMMS matrix. And so the up-type Yukawas will have this form. Now for the neutrino, right-handed neutrino Yukawa, things are a little more complicated, but you can assume a specific form proposed by Casas and Ibarra some years ago, because this form will again reproduce the type 1 seesaw neutrino mass matrix here. Now what's interesting here is that you have a new matrix here, which is complex orthogonal. Okay, so this is some unknown matrix. So mu is this light neutrino diagonal mass matrix. So you can make many different types of combinations of these Yukawas, but for our purposes, we only have these 4 matrices combination of the Yukawas, okay, that are relevant. So in this case, this is from the up-type Yukawas, up-type quark Yukawas. This is for the right-handed neutrino Yukawas, and these are from the charged lepton down-type Yukawas. Okay. For the quark sector, we know that the up-type, the top Yukawa is of order 1, and these are actually much smaller. But in the down-type quark sector, you have these Yukawas. These are actually very small also compared to the top Yukawa. So that means this BQ here matrix is negligible. The elements are negligible compared to the up-type quark Yukawa matrix. Okay, the elements of this matrix. Now for the neutrino part, you have some freedom here. Now in this case, as usual in the canonical type 1 seesaw mechanism, you assume that right-handed neutrinos are very heavy. So in this case, that's what we assume, and we assume that they are so heavy that you can make this assumption here. Now this charged lepton Yukawas are actually very small compared to 1. And so you can assume the right-handed neutrino mass to be very heavy, so that you have these relations. So in the end, then only these 2 products or the combinations, spurion combinations here, that are relevant for our purposes. And the most general forms, once you ignore these matrices, the most general forms are given by these 2 objects here. So these are the spurion building blocks that I will use when I have that I will insert into my new physics Yukawa. New physical Lagrangians. Okay, so this is now what we have for the Z prime scenario. So again, the general idea is that you want your new physics operators to be invariant under the flavor rotations I mentioned before, and also under the standard model of gauge symmetry. So this is the couplings that we want. So for the Z prime coupling. So the Z prime coupling here is given by, so this Z prime coupling interacts only with the left-handed quarks and leptons. Okay. So the MEV is imposed by this delta C. So this is the Z prime couplings, the Z prime interaction with MEV couplings. So these are the same objects as before, the deltas. Now, once we have this assumption, the operators, the two operators I showed earlier, actually not all of them can be generated by the Z prime. So only O1 actually is generated by this Z prime interaction. The O2 has charge current, so it cannot be generated by this Z prime. It turns out that once you have these couplings, you can also generate 4 quark couplings and also 4 lepton couplings. And so that means you need to consider constraints, experimental constraints on these different operators, the quark lepton couplings operators and the 4 quark and 4 lepton operators. Okay, so let me just consider those, the main constraints on these different operators. So for the quark lepton operators, once you have this O1 operator I had before, you can rewrite the effective value I showed earlier in this form. So in general, this can, for example, this one here can generate B to S L L prime. L and L prime may not be the same. Okay. So this can generate the B to S mu mu anomalies that I mentioned before, but also some other channels with different flavors in the leptons, I mean the final lepton, in the different final leptons. Okay. Okay. Now a little bit more details. You can expand this delta, these deltas, and so you have this form. And you can generate analogous formulas for B to D L L prime or S to D L L prime. So that O1 operator can contribute to various processes in general, low energy processes. Now from one of the earlier global analysis I showed, we have this global fit results. Okay, so as I said before, the new physics in the electron channel is assumed to be negligible. So that means the CE is 0. Okay, but on in the muon channel, you have this range here. This is a 2 sigma range from this paper. And so once you have these results, you can essentially explain the B to S mu mu anomalies. Okay. So this is what the values we will use as at least as input, and then we can also consider some other constraints. Now for the quark lepton operators, there are actually other constraints that one can consider. For example, mu to E conversion also gets contribution from that operator, but the current data are not yet stringent enough to constrain the couplings. Similarly, you could also consider lab data on E plus E minus 2Q, but in this case, because of the E channel assumed to be vanishing, we do not have any constraint. But you can also consider more recent LHC data, PP to LL, but again, these are not yet very restrictive at this point. Now for the quark-quark coupling, for the 4 quark couplings, at 3 level, they contribute to BP mixing. So BD mixing or B sub S mixing, and also Planck mixing. Okay? So we consider where these constraints. It turns out, well, these are the data for this P mixing quantity here. So the current data here and also the prediction for the standard model. So it turns out that the constraint from B sub D mixing actually is a little bit stronger than constraint from B to S mixing. But basically the result is that this combination of the quark Yukawa from the quark sectors, from the delta Q basically that I mentioned before, is given by this constraint. So this is the expression of the constraint. So I'm limited to this value. Oh. Okay. K-on mixing data actually produce a little bit weaker constraint. So this is what I will also use in my numerical analysis. Now in the lepton for the 4 lepton couplings, you also have constraints. So in this case, you can have constraints from charged lepton flavor violating decays. At the 3 level, for example, mu to 3e, it use some constraints on the couplings, but also the well-known mu to e gamma. Okay? But it turns out that mu to e gamma and tau to 3 mu e, tau to 3 mu can be very good constraint. Okay? At the loop level, also you have contributions from this Z prime to various processes, especially mu on G minus 2, where it turns out that the constraints is not very strong. But the Z prime cannot explain the mu on G minus 2 excellent, because only it's purely left-handed couplings can only produce a negative number, which is the opposite. It's the opposite to what you want to explain the mu on norm. Okay, so let me now, before showing you our numerical results, as I mentioned, we have this object delta L for the lepton, for the spurion object in the lepton sector, and the L is from the product of the right-handed neutrino Yukawas. And so you have this expression. So this O matrix is unknown, but it should be orthogonal and complex in general. Okay? And so you need to make a choice here for this O matrix here. So the simplest choice, of course, to assume it to be real. So in this case, this will be 1. Okay? But it turns out that for the simplest choice, the Z parameter space cannot satisfactorily explain the anomalies because there are anomalies. Okay? And so that means you need to make a different assumption for the O matrix. Okay? So you need to have a less simple structure of this Y nu. So it turns out that you can do that, you can have a better situation if you assume that this O matrix is complex. So if that's complex, you can generally write down this O dagger product here in this form, where R here is an antisymmetric real matrix. Okay? So essentially in this case, you have extra 3 parameters, which you can adjust. Okay? But it turns out it's actually very helpful. So it turns out in this case, we can have viable parameter space. Okay? So I'm showing you a scan of the results. Okay? But it turns out that because you also have a choice of whether you want the light neutrinos to have a normal or inverted hierarchy in their masses. Okay? It turns out that in this case, the inverted ordering or inverted hierarchy is preferred over the normal ordering. So this is the normal ordering case. This is the inverted ordering case. So the inverted hierarchy case is preferred. So that means this is testable, because if in the future this anomaly is being confirmed, and if the neutrino mass hierarchy is also determined, then you can check which one is preferred, which one is the correct one. Okay, now I'm showing you here some more results. So this is the ratio of calculated branching fractions compared to the experimental upper limits, current experimental limits, and this is the C mu coefficient I showed you earlier. So it should be between -1 to -0.3, like that. So as earlier also, that the normal hierarchy cases, inverted hierarchy, the normal hierarchy case is less preferred, but there are some correlations here for some of these numbers here. Okay. So again, these are actually some of these points. Many of these points are also predictions, because although some can saturate the current bounds, but there are others which are below the current bound, so they can be tested in future measures. Also, if these lepton flavor violating processes are discovered, you can also test the predictions. Okay. So these are again some of our results, but also predictions. And you can also make predictions for lepton flavor violating B meson and K meson decays. Okay? So we also have predictions. Now it turns out the data are not very stringent here, and also not very many data. So I encourage our experimentalist colleagues to consider these, to find these, improve on these bounds. Okay. So actually, most of these bounds are from more than 10 years, over maybe about 10 years ago. And so hopefully BEL2 and LHCb can improve on these measurements, these bounds. It turns out that although many of these are actually a few orders of magnitude below the current bounds, but some actually are within 2 orders of magnitude. So these predictions can be tested in hopefully in the near future. Some of these predictions. You can also make predictions. Predictions on lepton flavor violating Z boson decays. Okay, because we also have data on these. So the Z prime contributes via these loop diagrams to these processes, and so you can make predictions. And again, some of these are very close to the current bounds. Okay, so especially this one here, and this one here also. Okay, so this can be hopefully tested in the near future when these bounds or these decays are such. So that's the end of my slide, my last slide. So if the recently observed P2SL anomalies are new physics signals, then it is possible that they arise from a Z prime boson which interacts non-universally with standard model fermions according to the hypothesis of minimal flavor violation. Okay? And the application of MFV allows us to establish links among various lepton flavor violating decays as well as the neutrino sector. And we also able to make predictions for some of these decay modes. And some of these predictions can be tested hopefully in the near future. So that's the end. Thank you.
Thank you very much. Any questions?
So normally when we think about Z prime couplings, we focus on anomaly-free combinations and which charge are rational numbers, integers, and so on. So what is the UV completion you have in mind for the MFV coupling with Z prime?
Yeah, actually in this scenario I didn't mention, but our Z prime is not necessarily a gauge boson, so it could be in general any spin 1 Z prime. And actually we have not really considered specific
spin 1 what?
Spin 1 particle.
Okay.
So it could be a gauge boson, it could be some composite particle.
Then the cutoff is very close. Then you need to worry about those composite states, right? There are other composite states with flavor violation.
Well, it's maybe, but I'm assuming that they do not have any effects on negligible. They have a negligible effect on the properties we have considered. Okay. So I'm kind of agnostic about that.
So awesome.
You were saying that CEE equals 0 and this implies delta EE equals 0, right, on this fit. But doesn't this introduce like a large amount of fine-tuning to tune this, because then you need some cancellation, right, between the leading order and the flavor violating part. How precise does it have to be?
Yeah, well, some of these actually are fine-tuning this. So we don't worry too much about that.
Okay, let's move on to the next session. Please thanks to the speaker again. Okay, the next speaker is Shanwei Kang from Academia Shinika in Taiwan, and he will tell us about exotic state RDA 73.
morning. I'm very happy to come here to present our recent progress on the exotic hadron states. And a few of the audience here may have already listened to my talk. So previously, I want to discuss the heavy flavor meson decays based on my collaboration with Chris Biggie and also Professor Haiyang Chen. But then I found my topic discussed here is more relevant to the one discussed in this morning, especially for the Professor Eric Bratton and also Oki. I will use these two particles as examples, the ZB states and the X3872. In the first part, the only input is the pole position. And in second part, you will find some new surprise beyond the conventional virtual or bound state. As we know, more and more exotic hadron state candidate XYZ states are observed in experiment. And their interpretations are still mysterious. So many scenarios have been proposed, like the molecular, hybrid, or kinematic effects. And the most prominent one may be the molecular states, because we notice that these XYZ states typically stay close to threshold of meson pairs, around 2 or 3 MeV. For example, for the ZB above B bar threshold. So in principle, the effective range expansion works. And for ZB states, the PDG has already determined these quantum numbers, and isospin, G parity, and the total spin, and the parity. Okay, in this page, I only want to show the last 2 points and neglect these details. I want to see that the very simple model, the uncoupled channel effective range expansion, works at least as a first approximation. Because in experiment, the Bell has measured ZB to BB bar, the branching ratio is around 80%, only single channel. Okay. Now, in the effective range expansion, there are 2 quantities. One is a length of A and here, and the other is the effective range R. And for the resonance, the mass and the width can be also provided. So there's the 2 correspondence. You can solve the equation of A and R to reproduce the pole position. And then we can get these values of A and R. And these numbers are the uncertainties estimated by us. And although this model is very simple, but we want to mention that on one hand, it reproduces the pole position. And on the other hand, it can describe the data near threshold. And our selling point for this paper is the concept of the compositeness. The whole story should be dated back to 1960s. That's for the well-known relation for the deuteron. And if it is a pure bound state, the wave function generalization should vanish. And Z is called the elementariness, and X is called compositeness. And it's defined as in this way. And gamma is the residue. G is a 2-point loop function. And okay, and here if X equals 0.8, it means the 80% of that B is the B star bar components. And as in the last talk of Oki, he has mentioned the bound state appears in the first Riemann sheet, and for the resonance it appears in the unphysical Riemann sheet. So here, if you want to calculate gamma, the residue, you need to be careful. And however, for resonance case, if you want to calculate x in this way, you will find it's a complex number. Now, what to do next? We find that by making a phase transformation, we can redefine x in this way. But we have a condition that the ER square larger than the lightest here energy threshold. And in our case, the effective range expansion, we can adapt it to the non-reactivist case. And we know that at the pole positions, the momentum is also complex. We have a real and the imaginary part. And here we have the A and R. And in experiments, they can provide the mass and the width. So all these relations can be related to each other. Here is our value for the x. For the ZB state is around 80%, and for ZB prime it's around 70%. And here we make a big caution that a distinct feature for the effective range expansion is that, and here the effective range is in the neutral size. The neutral size means the pion exchange energy scales is around 1 Fermi, and here it is just so. But in some cases, the effective range will be huge. In that way, we will doubt the convergence of effective range expansion. So we notice that there's a more general two-body scattering amplitude. It is not invented by us, we should admit that. But first used in the XYZ state. Here I use a few words to explain how the CDD pole appears. The CDD pole is named after the discoverer, Dulles and Dyson and the first guy. You should learn of the words the crossing symmetry, analyticity, and unitarity. That means that there's a theory in the 1960s in Berkeley, like the very famous guy Jeffrey Chu, right? Before the quantum field theory. And you can implement all the quantities in the n over d method in dispersion relation. And in the n function, you have the left-hand cut. And in d function, you have right-handed cut and the poles. But before the dynamics of theory, there's ambiguity of the poles in d function. So it's here, you should implement the CDD pole. And in other words, in modern language, we can understand it better. This is done by Dyson, because the CDD pole is very important to distinguish the elementary and the composite particles. If CDD pole is very close to two-body threshold, it will result in a very small compositeness. In this way, we will see that it contains many other important components, like the compact quark-gluon state. If CDD is very far from threshold, you will get a large compositeness, like 0.8 or 0.9, as we shown before. Then it means it contains a large portion of two-meson constituents. If still hard to understand this, I will say that the CDD pole is a zero of amplitude of T. Because you see, if E equals mCDD, here it will go to infinity. And 1 over infinity is 0 of T. At that point, that at that point, it's the manifestations of the elementary particles. At the last two points, we show how it is related to effective range expansion. We just expand the real part, we can recover the ERE. At this point, you will see if CDD is close to threshold, the value of effective range will blow up. So, and certainly here's the expansion does not converge. I will extensively use this amplitude, or you can see it's a new parameterization of two-body scattering amplitude. We will apply it to the XYZ states. The X3872 particle is the first observed one in experiment, and it deserves our great deal of efforts. In 2003, Bell observed it, and now, up to now, it has already 1,400 papers. And the PDG has determined these quantum numbers also very well. And from now on, we will define the energy respect to DD bar threshold. And concerning its interpretations, as I already mentioned, it may be a molecular-like virtual state or bound state, or even pre-existing state. That means elementary, or the CC bar quaternion. Typically, these virtual or bound scenarios are based on the ERE analysis. The pioneering one is done by Hanhart, and also including Bratton. And here and in his paper, there's a concept error. It is pointed by Bratton. But as we mentioned that, if there's a nearby CDD pole, the ERE convergence will be dot. And we have shown this here, right? So if we use the new parameterization of two-body scattering amplitude, we will find beyond the conventional virtual or bound state, we will have a simultaneous virtue in second Riemann sheet and a bound state in first Riemann sheet. And also we find maybe there's high order S matrix pole. It is allowed by general S matrix theory, but not observed in the world. Before our analysis of the data, I will briefly review the experimental situation. And here's the D star data for the Baba and Bell. We also have Gypsy Pi data, Baba and Bell. And in this case is the PP Barclaysm from CDF. All the previous analysis do not include this data set. And also this data set has very high statistics because it's around 1 MeV. Okay, for experimental mental situation, we have the 2 data sets of D star bar and 3 data sets of Gypsy Pi. And we have shown that there's a new parameterization of two-body scattering amplitude. And here I again confirm that if CDD bar, if the CDD pole is very far, such that it can be neglected, you will recover the zero range effective range expansion that is extensively discussed by Eric Bratton. For fitting the data, we will use the D function. Okay, now we define a spectrum function. that is defined in this way. And the alpha is the residue of the D function, and the gamma x is a very small width of the pole position. You will find the right side is just a Breit-Wigner-like. So if it is a narrow resonance or the bound state, the integral is very close to 1. Otherwise, it's not. For example, if the shape div is the Breit-Wigner match, like the volatile state, you will not have this constraint or relation. And for the ERE relation, the integral does not convert, just cut off in the signal rate. Here, you will find it's 1 over k. Huh? Because our data set is the measured event distribution. So now we also provide our formula for that. This is for B2 gypsy pi decay channel. And the NBB bar is the total BB bar numbers. And the capital BG is the overall normalization constant. And CBG is the background. We just use linear background in the short rate. And here's R function is the Gaussian resolution function used by experiment. Here we also include the beam width effect. That is, all the experimental details are also considered by us. And for PP bar to gypsy channel, you just replace this event number by the partial cross sections. And here is a more complicated form for B to D star. It's first derived by Bratton, but in our paper we have more elaborate the details. Without mentioning it too much, we want to say the 2 points. One is that you can understand it by comparing to the previous one. If the gamma star is the D star width, it's very small, right? This around 60 keV. If this guy goes to 0, you will have a delta function. Then you will recover the previous equation. But now the D star width is important because it's always very small. Note that the X particle locus is also 0.1 MeV. It's not so small compared to the location. And in numerics, we also confirm this point. Okay, now we show how we fit. That's as I mentioned, these 2 overall constants and the background are fitted parameters in any case. And if the integral is 1, then the overall constant can be justified as a branching fraction. And in the D function, we only want to make a comment. Maybe one can use the more general D function other than the ERE. In the D function, there are these parameters: the CDD pole and its residue, and the subtraction constant beta. We find it may be redundant for fitting to reduce the correlation between parameters. Then we make these choices. For the first case, we just use the ERE, but making a combined fits. We want to do that because 2 purposes. The first is that we want to confirm our code works. The other one is the combined fits can constrain the parameters more stringently than the fit 1 by 1. In the second case, we impose a volatile state or the bound. In any case, I want to make my language very simple. like that, we want to provide some relations to constrain the parameters. In the third case, there's a simultaneous virtual and bound state. Okay, now it's the result of fit. It is hard to distinguish in the Jepside pi channel. And for DD star channel, it's also acceptable. But still there's difference near threshold. And here we list our numerical values for the populations and the compositeness and the residues and also the observed event numbers. The last line can be related to branching fraction by dividing the overall the total event numbers. In the first case, because we use ERE, it's a pure bound state. The compositeness is 1. And in second case, here is a double virtual state. And here is a triple virtual state. It means in the vanishing width of D star, these two poles converge together. And for the third case, it's a simultaneous virtual and bound state. In this case, you find the compositeness is very small, and here around 10%. It is more likely a pre-existing state. So that's we want to mention these 2 points again. If we want to use a more advanced treatment, we will get the new results. In the case 2, we find the higher order asymmetric pole. And so these residues are very large. And in the third case, we find in both the first and secondary Riemann sheet, there are poles. And also CDD is close to threshold. The resulting compositeness is very small. We also find that this conclusion agrees with Morgan. Morgan is a collaborator of Panington in GLab, and the Morgan criterion states that if there's a pole both in first and secondary Riemann sheet, the compositeness is very small. Most probably, it's a pre-existing state. In our case, we quantify this case is around 10%. Okay, I think now finished. I want to save 2 minutes for the lunch. Thank you.
That is open for questions. No questions? You want to have lunch earlier? Okay, if not, let's start to speak again. As we already heard, the lunch boxes are provided at the NCTS with, in different buildings, so please follow the local people. And please be back here on time at 1:30.